So to recall what we looked at in the last class, we saw this, the last thing that we saw was the different production steps in sand mold casting, right? A gist of what happens in sand mold casting, right? As I said, casting has many types, but the most common being sand mold casting, right? When it comes to bigger castings, right? So you have the sand mold casting, which is very general, popular. Okay. So this is what is the what do you call it? The different production steps that we have in sand mold casting, right? We'll see sand mold casting later in the slides, but before that, any doubts from the last class? Okay then. So you see, the most important element we can say in sand mold casting is molding sand, right? So we'll look at the properties that are required for the molding sand, right? So that we have a sound casting. And by sound, I mean the one which is desirable, right? Feasible. So what makes it feasible? The properties that are required will go through those properties. Okay. So molding sand is the most common utilized non-metallic molding material because of its certain inherent properties, namely all these, right? These are the properties that are there, and that's what we require in the sand mold casting process for the molding sand. Refractoriness, chemical and thermal stability at high temperature, high permeability and workability along with good strength, highly cheap and easily available, right? Because sand is uh, cheap and easily available. Certain kinds, not all. There are certain kinds where we have to mix up either different types of sands, or there are certain types which are very rare and therefore not so cheap. But the most general ones that we will use uh, is what is meant here, that it is cheap to find and available easily, right? So you see, just to give you the types of molding sand, although you don't have in the syllabus, but these are the types of sand, not just one sand we have, different kinds, right? Based on the geography and different locations, we have different kinds of sand, namely green sand, dry sand, facing sand, backing sand, system sand, parting sand, loam sand, and core sand. Okay. Now you see the properties that are required. First one being refractiveness. Defined as the ability of molding sand to withstand high temperatures without breaking down or fusing, and thus facilitating to get sound casting, right? Uh, because we deal with high temperatures, right? Molten metal, and therefore high temperatures. So it should be able to withstand those temperatures without breaking down, right? Should be able to hold itself together until the molten metal has solidified, right? So that's what makes us get a sound casting. Poor refractoriness leads to all these. What? Burn onto the casting surface, and no smooth casting surface can be obtained, right? The surface finish, as I said, the surface finish of the casting depends on, in sand mold casting, the surface finish of the casting depends on the molding sand, right? So if it has got no refractoriness or poor refractoriness, then the surface finish will be poor, poor surface finish. So that is what comes off as one defect, and burn onto the casting surface also. Degree of refractoriness depends on the SiO2, that is quartz content, and the shape and grain size of the particles. So this is quite in-depth, what do you call, analysis that they have found that the degree of refractoriness will depend on this material that they add. There are different materials that we add, right, to get this all these properties. So they found that the refractoriness depends on this material a lot, quartz content, the shape and grain size of the particles of these, right? Higher DSI to contain higher is the refractoriness of the molding. That's what they had concluded, right? Based on different experiments. Next thing is permeability, also termed as the porosity of the molding sand in order to allow the escape of any air, gases or moisture present or generated in the mold with the molten metal is poured into it, right? So porosity, as you know, is as for example your bone structure, right? It has got those tiny gaps, right? So exactly as that, you have the molding sand. Wherever you have, if you have observed, the molding after the sand has lost its moisture, right? Because of either keeping it in the sun or any other external heat that you apply, you observe the sand that it will be having some minute gaps, right? So that is what leads to porosity. I'm sorry, this permeability, that the air or the gases present can escape, and that's what we want. When the molten metal is poured and the molten metal is solidified, it will release certain gases because those gases are not soluble with the solid. They were soluble in the liquid state, but they are not soluble when it is turning into solid. So it wants to escape. Those gases or air, if present, wants to escape. The molding sand should allow the air or gases to escape. And the property of the molding sand which allows it to do is called permeability. Right? Is the concept clear? You see all these gaseous all these gases generated, I'm sorry, during pouring and solidification process must escape, otherwise this casting becomes defective, right? I've explained this why it becomes defective. No one? Because those gases would be present inside the casting, right? If they are not allowed to escape, it will either be on the casting surface or inside the casting. So you have voids, right? Basically gaps inside the material, solid material. So that's what makes the casting defective. Permeability is a function of grain size, grain shape, and moisture in clay contents in the molding sand, right? So grain size, if you have observed, finer is the grain size, finer would be the cavities inside, right? The gaps that you have inside would be small if the grain size is small, isn't it? Quite easy to understand, right? If the molding sand has these smaller grain size, then the gaps that you would see here would be less, right? In between. If it is coarse, you have more gaps. So common sense, right? So it depends on the grain size, the grain shape also. As you see there, I've drawn them more of a circular shape, right? Or sphere, if it is 3D. So it depends on the shape as well, right? Permeability is a function of all these things. Moisture and clay content, right? So if you control all these parameters, you'll be able to control the permeability, right? The desired permeability gets achieved. The extent of ramming of the sand directly affects the permeability. Common sense, right? If you ram it more, the gap inside or the gap between those two grains, right? I'm sorry, those sand particles, right, would be less. So more you ram it, basically apply a force so that it compresses, right? Compressing of the sand. So that's what affects the permeability, isn't it? So the ramming should not be too much, or it should be too less, right? It should be optimal, just so that we achieve the permeability that we require. If it is too much, if you have rammed it too much, the gap wouldn't be, there wouldn't be much permeability, and therefore the gases would not be able to escape. If it is too less, the sand would be, what will the problem? If we don't have, if we don't ram it enough, if we do less of ramming, less ramming force if we apply, what will happen? Let me call some names. One 58 Bharat. 158 Bharat. 158 Bharat. Not in the class. Yes, anyone? 199, 18H51, 199. 199. Not in the class. You see, if you ram it less, the sand strength would be less, right? Because there would not be there wouldn't be cohesion between the sand particles. That's why, right? So that's what makes it the less ramming force leads to lesser strength of the molding sand, right? Of the mold cavity that we have formed. Okay. Cohesiveness, right? That is what I was discussing. It is a property by virtue of which the sand grain particles interact and attract each other within the molding sand. Thus, the binding capability of the molding sand gets enhanced to increase the green, dry, and hot strength property of molding sand and porcelain. You see, cohesiveness, as we know, what is the difference between cohesiveness and adhesiveness? Yes, 157. You see, cohesiveness is the attraction between particles of the same kind. For example, sand particle with another sand particle, right? That's cohesiveness. Adhesiveness is the attraction between the sand particle and some other, maybe the flask, okay, the molding flask, right? So you get the idea, right? With the same uh, entity or with a different entity, right? Like sand with sand or sand with some other entity. So that's cohesiveness and adhesiveness. Okay. So cohesiveness is also required, right? The sand particles should stick to each other, right? So that you have this capability, binding capability, right? And we add certain binders also that we have we have good strength, we have good binding property. Okay. You see green strength. You have all these terms, not just strength. By virtue of this property, the pattern can be taken out from the mold without breaking the mold, and also the erosion of mold walls. right? Also, the erosion of mold wall surfaces does not occur during the flow of molded metal, right? That's what green strength is. So that when we are taking out the mold shouldn't break, and there shouldn't be erosion of mold walls during the flow of molded metal. Okay, that's what we indicate as green strength. Green sand after water has been mixed into it must have sufficient strength and toughness to permit the making and handling of the mold. As you can see, he's able to lift that, right? So it should have that strength and toughness so that we can handle it. For this, the sand grains would be adhesive. That is, they must be capable of attaching themselves to another body. That is basically sand, right? Sand with sand. Therefore, sand grains having high adhesiveness will click to the sides of the molding box. Right? Adhesiveness is between the sand and the flask, right? Or the molding box. Dry strength, as soon as the molded metal is poured into the mold, the moisture in the sand layer adjacent to the hot metal gets evaporated, right? That's thermodynamics going on there. That as soon as that molded metal comes into contact with the sand, which is at the surface of the mold cavity, the moisture or the water content in the sand exactly adjacent to that surface, right? The moisture gets evaporated, right? And this dry sand layer must have sufficient strength to its shape in order to avoid erosion of the molding wall, right? As more and more molten metal is coming in, that evaporated moisture, right? When it is left there, the sand should be intact even after the removal of the moisture because of the molten metal, temperature of the molten metal, right? So it should have sufficient strength to its shape in order to avoid erosion of mold wall, right? Otherwise, it will the sand would break if it doesn't have enough strength. So that's what we call dry strength of the molding sand. Okay. Dry strength also prevents the enlargement of mold cavity caused by the metallostatic pressure of the liquid metal, right? You have studied this in fluid mechanics, that fluids exert pressure, right, on the surface that they get in touch with. So because of that metallostatic pressure, right, of the molten metal, the mold cavity should be enlarged, right? That is prevented by having a good dry strength, right? So dry strength is also required to prevent this enlargement of the mold cavity because of this fluid pressure, metallostatic pressure. Strength of the molding sand depends on grain size and shape, moisture content, density of sand after ramming, as I said, right? All these things. Strength of the mold increases with the degrees of grain size and an increase of clay content and density after ramming. This also goes down if moisture content is higher than optimal value. So the moisture content, as I said, shouldn't be too high and too low. Should be optimum of an optimum value. Otherwise, the strength would go down if the moisture content exceeds. Right? If there is more water, right, in between the sand particles, that also acts as a kind of weak bond. Right? Instead of having a stronger bond between the sand particles, the water gets in between and forms a kind of weak bond between the sand particles, right? Every other sand particle. So that you lose the strength if you have more moisture. That's what is meant there. Is it clear? Okay. You see, another thing is flowability or plasticity. As it suggests, as the name suggests, ability of the sand to get compacted and behave like a fluid. It will flow uniformly to all portions of pattern when rammed and distribute the ramming pressure evenly all around in all directions. You see, when you are ramming it, if it doesn't have flowability, it will not reach the portions, the corner portions of the, what do you call, the pattern, right? Or this flask, isn't it? So it should have the flowability, that is ability to reach uniformly to all portions of the molding flask or the pattern, right? All around the pattern. And when we are ramming it, should be able to distribute, right? Even if it is not flowing or reaching those spots with just normal pouring the what do you call filling of the sand, it should be able to do so when we are ramming it. Right? Generally, sand particles resist moving around corners or projections. Right? In general, flowability increases with decrease in grain strength and decrease in grain size. You see, so all these properties are related. They should have an optimum combination of all these parameters to be able to get an optimum sand, right? Sand mixture. Flowability also varies with moisture and clay content, right? Adhesiveness, right? As I was talking about, a property of the molding sand, and it is defined as the sand particles must be capable of adhering to another body, right? Not in between one another, that is cohesiveness, in between the sand and other body, maybe flask, pattern, or any other entity, okay, core, etc. So there only the sand should be easily attached itself with the sides of the molding box and give ease of lifting, right? Turning the box when filled with the sand. You see, so if there is more adhesiveness, when we are removing the pattern, that sand would come with the pattern, right? All the surfaces that are attached to that pattern will have erosion of the sand. So if adhesiveness is more, you will have that problem. But it should be optimum, right? It should be 2 less, just as other parameters, right? So optimum adhesiveness is also required. Okay. Another thing is collapsibility. As the name suggests, the ability of the molding sand to collapse. Right after the molding metal is if the mold gets solidified, the sand mold must collapse so that free contraction of the metal occurs, and this would actually avoid the tearing or cracking of the contract metal. Right? Because when let me show you here. This is your core, okay? This is your core. Okay? When sand is around it, you see, let's say this is the sand around it, okay? I'm drawing a random shape. All this is sand. Or maybe I should draw it like this, right? This is the seat of the core so that it doesn't fall down. Okay. So the sand is around it, around this core. So you see, when we have removed what do you call? No, actually, this is after the pattern is being removed. Okay, all around you have sand. Let me clear this, and now I will draw. This is the sand around it. Okay, we had placed a pattern here, right, in this particular spot. We had placed a pattern, right, and then removed it. So all you have here is a mold cavity, right? Once the pattern is removed. So now when you fill in the molten metal, right, that molten metal is filled down. You see it is solidifying. Now, when this core, you see when it is solidifying, it will try to contract, right? That's what leads to shrinkage. When it is contracting, it will try to put some pressure on this core, right? Let me use another color, maybe black color, right? It will put pressure on this core. So if this core doesn't collapse, then this molten metal will have defects. That's what is meant here. All these defects that you're seeing, tears and cracks, will happen if this core doesn't collapse because of this pressure from the molding sand, right? When it is shrinking. Okay. So even collapsibility is required, that it should collapse. This core should collapse upon solidification, right? Or otherwise, if it doesn't collapse right when it is solidifying, it should collapse when we are removing it. Once the casting is completely solidified, it has come down to room temperature, and we want to remove the casting. Now we don't want this core anymore. We have made it to be collapsible. So that collapsibility property is also required now, right? So that's what is meant here. This property you see is highly desired in cores. This exact example is what is meant here at this point. Am I clear? Right? You see steps involved in making a sand mold. Okay, how do you make a sand mold? All these are steps. Quite simple. You have seen the video, right? So all these points are basically trying to describe the same thing. That process that we saw in the video that I showed you, probably the second class, right? You see here, creating of the pattern, placing a flask over the cope portion of the pattern. You see this flask, filling the flask with sand and removing the cope pattern, right? Now place flask over drag portion of the pattern, fill it with sand, and then remove the drag pattern, right? So all you have is a cavity there, as you can see. Now assemble core in the mold, right? That cavity will try to assemble the core, as you can see there. Then assemble the cope and drag, right? Now pour metal into that mold cavity, right? Assemble the cope and drag in the sense, try to align this two, okay? Now, when you pour model metal, that's what you get, right? All these are what do you call auxiliary component, accessories, right? Screw, gating system, runner, etc. What was required was this, right? Or maybe this also. So shake out mold and trim off the gating system, or that gating system will be trimmed off. So you get the casting. You see here, suitable size of molding box selected, suitable wall thickness, so that when you are ramming, etc., it shouldn't break. Sufficient care should be taken in such that sense that the molding box must adjust for cavity, riser, and the gating system. That is, your gating system includes your screw, runner, and gates, right? And then, as we have seen in that image, placing the drag portion on the pattern, with the parting surface down on the bottom, as shown in figure 12.6a. This is requiring this. Okay, you have placed the drag pattern, right? This is your drag part, right? That's what we're calling drag. And the portion of the pattern, the half pattern that we will put in drag, is called drag pattern, right? Don't get confused. The portion of the pattern, we have two patterns, right? Top and bottom, basically two halves. So one half is called drag pattern that we'll keep in the drag, right? And so that is what is meant there. You put that, and then you put the molding sand, and then you take it upside down, right? Turn it upside down, and then you take out the drag pattern, right? That's what you do. You pour the molding sand, ram it, and then flip it right upside down, and then take out the drag pattern. So all you have is a mold cavity there and the rammed molding sand, isn't it? Similarly for your coke, right? And then for the coke, you put these screw pins, all these